This is the first worksheet in your new packet. Everybody good? All right. If you've had physics, hopefully you've all at some point talked about vector quantities in some science class at some point, but if you're in physics or have had physics, you've done a lot of this. All right. Many physical quantities such as speed, distance, etc., can be expressed by a single number called a scalar. This number indicates the magnitude or size of the quantity. We're going to use the word magnitude. Okay. A vector is a quantity that has both magnitude and direction. So you need to be able, the first 6 questions on the homework are just, is this a vector or a scalar? All right. A vector has to have direction and size or magnitude. The velocity of a football is a vector that describes both the speed and direction. If the guy kicks the ball at 20 feet per second, which is probably really slow, I don't know, and at a 60-degree angle to the ground, that would be describing that as a vector. Sound familiar? We just did that with parametrics, right? All right. You don't have this on your notes, okay, but here's some examples like numbers 1 through 6 in your book. State whether this is a vector quantity or scalar quantity. A boat traveling 15 miles an hour. Yeah, it only has magnitude. It doesn't have direction, so therefore it's a scalar. Everybody okay? A hiker walking 25 paces due west. We don't think of paces as a magnitude, but it is, okay? It's a length, distance. And he's going due west. So that is a vector because it has magnitude and direction. Everybody all right? This is the one that I would not put on a test or quiz because I'd get it wrong. It says a person's weight on a bathroom scale. It is considered a vector because weight is due to the force of gravity, which is downward pull. I would have gotten that wrong in a heartbeat. So that will not be on a quiz, okay? Here are some examples more like what's on the homework or in addition. So a car traveling 60 miles per hour, 15 degrees east of south. What do you think? Vector because it has magnitude and direction. Everybody okay? A parachutist falling straight down at 12.5 miles per hour. It is a vector because straight down is a direction. A child pulling a sled with a force of 40 newtons. It is a scalar because we don't know, is the 40 newtons straight horizontal? Is there an angle to the rope on the sled? Okay. So make sure we got these right. We're good? Vector, vector, natural direction, so scalar. All right. This is some vocabulary that you need to understand about vectors. A vector can be represented geometrically by a directed line segment. All right? It looks like a ray when we draw it. The difference is a ray is said to continue on. If this is called a vector, and sometimes they'll draw a little line at the end to show that it's a vector, it means it ends at the tip of the arrow. Okay? It has an initial point, also known as the tail, and a terminal point, also known as the tip or head. The vector, if this had been this example over here where it has initial point A, terminal point B, the arrow is where it ends, then they will write it like this. I don't know if you can see that, but a lot of times they use a single arrow, like a half arrow on here to denote it's a vector. If they put the full arrow, then we might think ray, right? All right, if a vector has its initial position at the origin, it's called standard position. We're going to measure a lot of things in standard position off the positive x-axis. The direction is a directed angle between the vector and a horizontal line using the positive x-axis. The magnitude is the length that you draw the vector. Now, pay attention for a second here, but I will tell you, I'm not going to require you to do this. They say if we want to represent, what are they representing? 13 feet per second. You have to choose a scale. So you say 1 centimeter is 5 feet per second. You divide that and you get 2.6 centimeters. And then you would have to accurately draw this as 2.6 centimeters, but you would label it as 13 feet per second. And the scale would indicate what, I'm not doing all that. I'm just going to have you draw an arrow and label it 13 feet per second, okay? You don't have to accurately draw it to some scale. Would be here for a week. All right, so some of that vocabulary is at the top of your notes. In a minute, we're going to talk about bearings. This is the part of the lesson and the part of vectors that students really struggle with. I will tell you there is not a bearing question on next week's quiz, okay? We're going to kind of spiral this idea, do a bearing question every day until we get the hang of it. Does that make sense? And then put it on the quiz after that. A quadrant bearing is what they call it, is a quadrant bearing, or directional measurement, is between 0 and 90, east or west of the north-south line. So when they write it like this, it means you start at south and go 35 towards the east. When they use this notation, they're always going to start off of either north or south. Now, that being said, there's an example in a little bit where it says something like 30 degrees west of north. Okay, that's spelled out clearly, wants you to go off of north to the west. Or it could be 20 degrees south of east. That's saying start at east and go 20 degrees to the south. When they use this notation, where it's letter, number, letter, they want you to start off of north or south and go towards the second one. A true bearing is a directional measurement where the angle is measured clockwise off of north, okay? This is my understanding. This is what air traffic controllers and such use, okay? Off of due north, they measure around clockwise all the way to 359 degrees. All right. When you use off of northwest, south, or east, you can't go over 90, right? Because then you're into the next quadrant. But a bearing, if you said 310 degrees, a bearing of 310, that means you're going off of north all the way around here, and you're going in that direction where there's a 50-degree remaining angle in there, okay? We'll practice with those ideas. This is what you're going to have to do on the homework. It's going to say draw 20 feet per second in a bearing of 030. So you're going to go like this. And then you're going to say bearing of 030 is off of north. When they use that, I don't think I talked about that. Did I read that carefully to you? It says they use 3 digits. Whenever you see the 3 digits starting with a 0, it does mean off of north, okay? But basically, I would tell you probably there's just a true bearing or whatever. But 30 degrees, so you would mark 30 degrees in here and indicate that this is your vector. And then you would label it 20 feet per second and be done. Okay, I'm not going to make you do a scale. This question said 30 miles an hour at a bearing of, where do I start there? S60 west, what does that mean? I start at south, and the 60 degrees it's going is towards the west. So you'd put your 60-degree angle in here, and you'd label this 30 miles per hour. Any questions about how we're drawing these? So let's do 4 of them together. You have these, so you need to be doing these on your paper. 60 pounds of force at 125 degrees to the horizontal. It said in several slides ago when it says to the horizontal or standard position, it's starting where? Positive x-axis, okay? So it's measuring off of here, 125 degrees around here. And the vector is here. It's not that curvy thing, and it's not the x-axis. There's the vector, and along the vector, you can label 60 pounds of force. Just 60 pounds is fine. Easy peasy. Okay. Do a couple more off different things. This one says 55 miles an hour at a bearing of, what does this mean to do? Start at south, which my line is really crooked, and go 45 towards the east. So it would be 45 here or here because it's 45, but so this is the vector. You don't have to do anything special to indicate that it's the vector other than just make sure you're not putting arrows on a whole bunch of stuff so I can't tell which one's your vector. And then it should be labeled 55 miles per hour. So far, so good? So can you try these two? Quick sketch. I can't even use the line tool and draw a straight line. So this off of north, 45 to the west, this is not a very good example because again, it's 45 either way, but this is where it's describing, right guys? And then you'd write 30 meters and 150 yards at 40 degrees to the horizontal. The 40 would be in here and 150 yards. Did I just say meters or was that the last one? I don't know what I said, but are we good? That's what you had? Okay. We're going to talk about going back and putting components on those in just a minute. But first, just a quick overview. Parallel vectors mean they have the same direction and magnitude. So which ones in this, I'm sorry, same direction only, lied. Which ones in this picture are parallel or not? It says same or opposite direction. Okay, my bad. So everything but D is a parallel vector. Equivalent vector has to have the same magnitude and direction. So which ones look like they're going the same direction, same length? A and C, okay. Opposite vectors mean they are exactly opposing forces, so they're the same length, but going in exactly opposite directions. C and E or A and E, seem okay? All right. We do have to be able to find components for the quiz next week. Rectangular components are just XY components, usually written like this, though I'm not sure the book uses this notation until section 8.2. This is going to be your horizontal component or your X, and this is going to be your vertical or Y component. Make sense so far? All right, in a picture like this, it says the force exerted by pulling the wagon here has both a horizontal and vertical component. We just make a little right triangle. So for this question, if Heather's pushing the handle of a lawnmower with a force of 450 newtons at an angle of 56 degrees with the ground, how would you find X? Someone tell me how you would find X. Okay, so right triangle, so we can use SOHCAHTOA trig, yes. This is adjacent and hypotenuse is known. So we could say the cosine of 56 equals adjacent over hypotenuse. And we'd end up taking 450 times the cosine of 56 degrees. And that would give us which, horizontal or vertical? Horizontal, yes, the X component. And to find the Y, we would do the same thing, but use what? Sine, right? And the Y, of coordinate and the sine would give us the vertical component. All right, you have a question on your sheet that is done for you already, but it says Jamel's pulling a rope at an angle, or tied to a dinghy with a force of 50 newtons at an angle of 60 degrees with the horizontal. So again, to find x, you would use cosine. And after you did this question, I'm trying to lead you to see there's a pattern here, guys. You would do cosine of 60 equals x over 50 adjacent over hypotenuse, and you'd end up doing the magnitude times the cosine of the angle. Everybody good? When you do the y, you would have sine of 60 equals opposite over hypotenuse, or the magnitude of the vector times the sine of the angle will give you the vertical component. This is always true as long as you are using an angle with the x-axis. If you were to draw this differently, if you did this, does this make sense? If you had here a 20-degree angle, which it would be 30 on this picture, but if you had this angle opposite and adjacent, this is still x because it's a cross, but now it's opposite, right? Which messes with us because we're used to x and cosine going together. So if you always draw your and measure the angle off the x-axis, these definitions will be true. The magnitude of the vector or length of the vector times the cosine of an angle with the positive x-axis will give you the vertical component, and the length of the vector, the book I think might use this notation for this section. Now, why might I use R? Well, several reasons. When we do this in polars in a couple of weeks, actually the end of next week, when we start polars, it's called the radius R. The same notation. We use T. Did we do T cosine theta and T sine theta as parts of our parametrics equations? Okay. So whatever letter we use, I just used R because it's the same thing we're going to do next week. But it's the length of the vector. But the important thing here, it has to be with the x-axis, and it has to be with the positive x-axis unless you want to worry about changing signs all the time. All right, this is on the back of worksheet 1. Did I skip the slide where it said go back and do this? Oh, right there, look, go back and do this for 1 through 4. Okay, sorry. We're going to go back and do this for 1 through 4. All right, the components. First of all, is the angle 45 that we started with right here, is that with the positive x-axis? No. If we want to make the angle with the positive x-axis, what could we call that? It is a 45-degree angle. If you call it positive 45, that's going to give you 2 positive coordinates. Does this point out here have 2 positive coordinates? No. If we call this negative 45 degrees, then it knows we're in the fourth quadrant, and we will get a positive negative coordinate, okay? So we could do some crazy draw the triangle, call this X, call it Y. But what I'm telling you is if you want to just call that the length of the vector, you can type 55 cosine of negative 45 degrees and 55 sine of negative 45 degrees. And you will get the vertical and horizontal and vertical components of this vector, which you can write like this as far as I'm concerned. So 55 cosine of 45, making sure your calculator is in degrees. What'd you get? 38.9, yes. And negative 38.9 when you did this one? Okay. Does that put it in the right quadrant? If I go right and down. Okay. I'm not going to label those numbers. If I were to write it on here, 38.9 and negative 38.9, because the negative number we were taught can't be a distance, right? And sometimes these represent distances, though this is speed, but they're just the breakdown of the components of the vector. All right, so what are we going to do on this one? Oh, did I skip 2? Oh, I skipped 1. Well, let's go back and do 1. Sorry about that. Which number do we want to use on this one? For the angle. Yeah, it's off the positive x-axis. This would put us into quadrant 2, which will give us the proper signs. If you wanted to use the 55-degree angle over here, you could, but then you'd have to remember to make the x negative and the y positive. By just doing 60 cosine of 125 and 60 sine of 125, we'll get the proper signs for the components. Anybody get answers? The horizontal component is what? Negative 34.4. Just clarifying which is horizontal and which is vertical again, because I think on the quiz it actually asks for one question, it says give the horizontal component or give the vertical component. It doesn't ask for both, and you got to know which one's which. Yes. Whichever is going to get you into the right quadrant. The other one we wanted quadrant 4, so we went negative. We could have also, on this first one, Courtney, this one that I did number 2, we could have also called that 315. We could have gone all the way around, and it would have worked. Does that help? What was that? Okay, everybody's all right though? Thought someone fell. Okay. Let's finish these 2. Can you do these 2, guys? What you gonna use for this one? Yes. You can do, yes, that's a great question. You can do it as right triangle trig over here, but then you'd have to you'll get the same numbers, but you would have to remember to put the negative on here because it will just give you these distances. I didn't even finish that question. What was it, 49.1? You would have to remember that that one should be negative because you were in that quadrant. But yeah, it's the same. It's the same. Good question. Where were we at? Number 3? Okay. What do we want to use if we want to just use our shortcut method here? 135, yes. 90 plus 45. I'm thinking it's the same number, yes. 21.1 and 21.1. The 45, 45, 90. Someone else get that? Do you get those numbers or am I crazy? Oh, yeah, it's 21.21. I am crazy. Can't read calculator. Better glasses would be good. All right, what are we going to use on this one? Just 40. So can you do that one quick? So if it asked only for the horizontal, 114.9, did someone get that?
Yep.
And if it asked for only the vertical, you would do 150 sine 96.4. I'm just trying to make sure you understand which one's horizontal and vertical. If you think about it, you'll get there. I always say the words backwards and get myself confused. All right, moving on to the back of the worksheet. Again, it goes through the bearings idea, okay? If you have something like this, this means off of south 35 towards the east. If they call it a directional bearing or a true bearing, did I just make that confusing? What was this one called? Yeah, that's quadrant bearing. Okay. This, if it's called a true bearing, or it'll just say off north sometimes, okay? Then it's going around clockwise, which is not the way we do when we measure angles, right? Got to keep that straight. How many of you have had the trig class so you did bearing questions and hated every minute of it? Yeah? They're hard. I'm going to try to get through one today that you can just watch, and it's hard. It's a lot of geometry going on. All right. Draw a diagram that shows the resolution of each vector into its rectangular components, then find the magnitudes of the vertical and horizontal components. So this is just combining what we just did. Okay. This one's from the horizontal. So we're supposed to go 7 inches at a bearing of 120 degrees from the horizontal. That seemed pretty good. How are we going to write the components for that one? The angle's already off the x, yes? Anybody got the first one? Negative 3.5, yes? And the second part? If on this question, if it didn't say from the horizontal, then it would be off of north, yes. No, because it says no. Yep. When it measures off the horizontal, it usually goes the way we're used to. It does go the way we're used to. Good question. All right. One more of these guys. This is, what does this mean? Yes. Off of north, 50 degrees towards the west, just a little more than halfway here. 2.5 centimeters per hour. Now, what are we going to use for the degrees this time if we want to do components? We don't want to have to worry about sines. We're going to need to use what angle? So 2.5 cosine of 140. Anybody already have that for me? And 2.5 sine of 140 should be positive. Because this was off of north, 50 towards the west, so the 50 is in here, so we're adding the 90. Is that better? Yep. What was the second component, guys? 1.6? Thank you. All right, we good? All right, I don't like this question. They tried to make an application question, but part of it is ridiculous. It says Nadia is pulling a tarp along level ground. Okay, so she's not going up a hill or anything. It's a force of 25 pounds directed along the tarp the tarp makes an angle of 50 degrees with the ground. So she took a piece of cloth or a tarp or whatever, and she piled something on it. At my house, we do yard waste. We throw on there, like if you're pulling weeds, then you pull it out to the pile in the back of the yard. Okay, so she's making this, has a 50-degree angle with the ground, and she's using 25 pounds of force along there. It says find the vertical and horizontal components. That makes sense to me, right? But the question goes on to say, what is the magnitude and direction of the resultant? That is the resultant, guys. So the magnitude is 25 pounds of force. Whoops. I would never ask this question. And the direction is 50 degrees from horizontal, or just 50 degrees. All right, how do we find the components though? What's the horizontal component? 25 cosine of 50, somebody have it? Okay, and the vertical, which was 25 sine of 50. All right, and you can write it, with those little arrowy parenthesis things, I'm fine. All right, now I'm going to get to some crazy business stuff that we're going to revisit several times over the next few lessons. When two or more vectors are added, their sum is a single vector called the resultant. The resultant has the same effect as applying one vector after the other. Geometrically, the result can be found using the triangle method or the parallelogram method. The triangle method is called tip to tail, and you use law of sines and law of cosines. I think that's what you're taught in physics, okay? The parallelogram method is a little bit different. It's tail to tail. And I honestly generally use what's just the component forms. All right, so I'm going to first of all show tip to tail, or I'm going to attempt to. Just watch, please. You don't have this question. An airplane is flying with an airspeed of 310 knots at a heading of 050. So where's there a 50-degree angle? Yes, this a heading of 050, there's 50-degree angle here. Everybody okay? So this would be 40, yes? Some geometry at work here. All right, and that was 310 knots. All right, a 70-knot wind is blowing from a true heading of 125 degrees. Same thing off of north, worded differently just to give us a headache, okay? But it's off of north 125 degrees. The part that students struggle the most with is from. I always draw a little picture of the wind because when it's blowing from that direction, you do not go around 125 and do this because it's not blowing it that way. It's coming from that direction, so it's actually blowing it this way. Does that make sense? Now, it says here it's blowing from a bearing of 125, so the vector is drawn so the tip points toward the north-south line. Had it been blowing at a bearing of 125, that would have pointed away from the north-south line. Is that what we did? We pointed, the tip is right here. You can see the blue one. It's pointing towards it, which is actually going to be extended this way. All right, when we use this tip to tail method, back here, do you remember what this angle was? This was 50, the whole thing from the north-south line, okay? So this one down here was 40. The tip to tail method says you would have to move this vector up here These are parallel. Do you remember the symbol for parallel back in geometry was to draw little arrowheads showing that they're parallel? Okay. So these two are parallel. We're trying to find this angle up here in between these then. Okay, I'm going back to this picture. It said a heading of 125. Help me here. Does everybody understand that's 125 degrees then? It's off of north. What's 125 minus 90? That makes this a 35. You good? Okay, back to my other picture. This is 35. If I put an east-west line right up here, above how do I want to describe? Okay. This, I don't even need to put that line in. I think you can get this without that line. Do you remember doing this in geometry? If these are parallel, these are called alternate interior angles, yes? They make the Z. So it goes blue, red, blue. If the blue are parallel, this whole angle right in here that I'm coloring green is equal to this whole angle right up here, yes? Alternate interior. So how much is that? 75 degrees, okay? The length of the blue vector, I didn't label, but back here it said it was 78 knots. So we're going to label this 78 knots. And this was 310. Does that sound right, guys? The plane? Okay. We need to solve for this, the actual resulting path of the plane. If I have two sides and an angle in between and it's not a 90, what do I have to use? Law of cosines. Okay? So help me find this distance. Type it in your calculator. Do you remember how it goes? One of the sides squared plus the other side squared minus 2 times 78 times 310. All still multiplied. That piece right there, I did a crummy job, okay. Knew I was in trouble. I started writing it up and down. Times the cosine of 75. Okay, type that in and don't forget to square root at the end. Okay, wake up and do this because otherwise you're going to fall asleep and not understand anything about this, which is, since it's tricky anyway. Okay, before I square rooted, I got 89,667. Anybody? After I square rooted, 299.4. That is the length of this. What does that mean? Yes, the plane is now traveling that speed. Let me explain. If he's trying to fly 310, but the wind is pushing him 78, doesn't it make sense when at that angle that it's going to slow him down a little bit? So he's down to 299.4 knots. The other thing it wants to know is find the direction of the plane relative. It says relative to the ground, but that's not really what they did. They did a bearing. I guess that's what they called it. But we need to find this little angle in here. Well, this little angle off of north is our question, okay? Any ideas on how to find that? Right down here, if we can find this one, I'm going to call it alpha. Do you see what I'm talking about? That angle. It's not 50, right? Because 50 goes all the way to the north-south. If we can find that one, okay, so the sine of that one is across from 78. In the same way, the sine of 75 was across from 299.4. Can you solve that real quick? 78 times the sine of 75 divided by 299.4. Then what do you have to do at the end? inverse sine. Nice use of vocabulary. 14.6 degrees. Anybody get that? Okay. But that's in our triangle. We want off of north. So what do we have to do? Subtract it from 50 to figure out what that little slice is that's left there. What'd you get? Okay, here's their answer. 299.4 knots at about 35 degrees off of north. Is that what we got? Painfully. Okay. I'm going to stop there. You can do, we will, oh, I should have done this question, but I'll be nice. It's Friday. We'll come back and do this one on Monday. But on page 488, guys, what you can now do is 1 through 10, okay? Those will not take you but 5 minutes. It says, is it a vector or a scalar? And then draw it and give the components, okay? The applications we'll work on some more Monday.